Alright, so here's the Lagrange multiplier video corrected. In this video I used ChatGPT, and I'll show you the rest of it, but corrected this time. So here's going to be what ChatGPT said. And as you can see, I asked it nicely, so that in the future they don't rebel against us, to give me this proof in multiple dimensions, which sounds really cool. Because, you know, I like multiple dimensions and high dimensional space and all that tesseract stuff. It's pretty awesome. So, yeah. And you may proceed to read further if you want. And you may proceed to read even further if you want. However, you may have noticed that not all steps were explained clearly. Well, actually, you probably didn't notice because you probably didn't even read it. That's okay, that's okay. Don't worry about that, because I'm going to show you how it's done for real, because there are also a few errors. So I want to correct all that stuff before you think that this is the right way to do it, which essentially it is, but I'm going to correct it just a little bit, or a lot, actually. Alright, so here's the presentation, and the following will be the proof done my way, instead of ChatGPT's robotic, stupid, well, not stupid, well, it's pretty smart actually, but you'll see my way. So the first step in finding the extrema of a multivariable function is to set the gradient to 0. For function f of x, where x is a member of x1, x2, all the way to xn transpose, we want to find x bar as a member of all x's such that the gradient of f of x is equal to the 0 vector. And that means that the partial derivative of f of x with respect to xi, the ith x, is equal to the scalar 0.
As you may have noticed, I have headphones on now. So we want to optimize, or minimize / maximize, xn plus 1 is equal to f of x, subject to constraints g of x is equal to the 0 vector, where x is all the x's in this vector transpose, and g is all of the functions, or the constraint functions, transpose. Whoops.
So now hopefully my voice is better now, because before it was sounding like a robot. Does it still sound like a robot? I don't know, we'll see. But let's focus on the constraints g of x is equal to 0. Effectively, what these constraints do is make certain variables in the domain dependent on the others. For example, g1 of x1, x2, x3, x4 all the way to xn is equal to 0. Is equal to, this implies that x1 is equal to h1 of the rest of the variables. And similarly, if you have g2 of x1, x2 all the way to xn is equal to 0, then you could rearrange it to make it such that x2 is equal to h2 of the rest of the variables. So you could do this for any variable you want. Basically, you're taking one variable in the domain and you're setting it, and you're making it dependent on the other variables in the domain.
And we can combine these constraints such that we reduce the dimensionality of the input to that of the rest of the variables that were not defined as functions of the others. Now I know that sounds like a mouthful of jumble, word salad, but it's actually not. And I'll show you exactly what I mean. So if we have g1, g2, and g3 as functions of x1, x2, x3, all the way to xn is equal to 0, then basically what we can do is that, we could do this for any variable, but let's choose x1. If we can basically say that for g1 as a function of x vector is equal to 0, we can basically say that we can pull out x1, and we can say that's a function of the rest of the variables that are not x1, like x2, x3, x4, all the way to xn. And let's say that we do this with g2 also. We pull out x2 this time, and we're saying that x2 is a function of the rest of the variables, and we do this with x3 also and g3, and so on. So basically, what we can do through some algebraic manipulations is say that we have x1, x2, and x3 defined like this. So basically, through algebraic manipulations, we can say that x1 is equal to h1 of, a function of x4 all the way to xn. X2 is a function of, h2 of x4 all the way to xn, and x3 is a function of x4 all the way to xn. So basically what we've done is that we've removed the dependence of x1, x2, and x3. We removed them from the domain. So that's what the constraints do. That's what they serve to do functionally in this context. And you'll see what I mean later. So going off of what I was saying earlier, we can actually generalize this concept such that if we have m constraints, then we can express the m variables in terms of the n minus m other variables. So for example, if you have if you define x1, x2, and x3 based on g1, g2, and g3 constraints, then so you have m constraints, you have 3 constraints, you have n x's in there in the domain originally. That's x1 all the way to xn. You can express each one of those dependent variables, x1, x2, and x3, as n minus m other variables, or n minus 3 other variables, which would be x4 all the way to xn. So what we're going to do is that we're going to express the first m variables as the independent variables, and the last n minus m variables as the dependent variables. So what I mean by independent and dependent is that the dependent ones are the ones that are defined through the constraints, like we did on the last slide, and the independent ones are the ones that are left. So that's going to be the convention throughout the rest of this presentation. And just to ingrain this concept of independent and dependent variables in your minds, if we have xm plus 1, m plus 2 all the way to xn is a function of hm plus 1, m plus 2 all the way to hn of the variables x1 all the way to xm, which are the m independent variables. Well, those are the dependent variables to the left, and those are the independent variables to the right. So the constraints tell us how to parameterize the objective function f of x, or that is the function that we're trying to optimize with respect to the constraints. And so you may ask, what do you mean by parameterize this function? Well, here's what I mean. We're going to create a new function, f tilde, that will be the parameterized version of the function f. So f tilde of x, which will be the independent variables, x1 all the way through xm, or sorry, that should be x1 comma m, will be f of all the independent variables plus the dependent variables as a function of the independent variables. Sorry about the uhs. That's funny. So x is going to be x1, x2 all the way to xn again, and then x1 comma m is x1, x2 all the way to xm, both transposed. So we want to optimize f tilde. That means that the gradient of f tilde as a function of the independent variables, which remember are the first m variables in the domain by convention. Doesn't have to be, you can always rearrange them, by the way, is going to be equal to the 0 vector. So, how do we do this? Well, here's how you do it. You take the partial derivatives, and that's equal to all that stuff right there through the chain rule, where I goes through all of the independent variables, and j goes through all of the dependent variables. And each one of those I independent variables, for each one of those, you're going to have the partial derivative of f tilde of x of 1 comma m with respect to xi is equal to 0. So now we have this over here. That implies that all that stuff is equal to 0 through the transitive property of equality. Kind of obvious, but you know, it's part of the proof. All right, and so now we get this over here. If we just rearrange the equation. So now let's keep that result that we just got in the back of our minds, and let's now shift our focus to the constraints, where g of x is equal to 0. Therefore, you get all these partial derivatives that equal to the scalar 0. And we have defined a new variable k. K is just a one of those, I guess you can call them index variables, where k is equal to m plus 1, m plus 2, all the way to n, just like j, except it's just a different index. And then again, as part of the proof, we use the transitive property of equality to say that part is equal to 0. So now what we're going to do is we're going to convert this to matrix form. So since we have a summation, we can actually turn that into matrix multiplication. And by the way, I'm not a mathematician, so I don't know if I'm doing this correctly, but it still works, so I'm going to do it. So notice that for the top equation, you can think of it like elements in the numerator vary across the rows, and elements in the denominator vary across columns. And if you think about it that way, then we get the correct result. As for the constraints equation on the bottom, we have the partial derivative of g sub k of x with respect to xi plus the rest of that stuff is equal to the scalar 0. So what we're going to say here is that if we have I and k represent the like how should I say this, like, where is the analogy? I don't know any kind of analogy. I was going to say book, but like that's more for just one dimension. Like a two-dimensional book where you go through pages two-dimensionally. Anyway, so if you think of I and k as some kind of index to locate your position, and j as a variable that that varies for each I-k combination, then you'll see that we have a scalar plus a row vector multiplied by a column vector. And so those cancel out to a scalar, and if you add those together, then it's equal to 0. So for the bottom equation, we're going to rearrange it slightly. And then we can do this, because since we turned it into matrix form, we can do the inverse of a matrix. And so guess what we can do? Well, guess what we can do? We can sub the matrix on the left-hand side into the top equation. We shall proceed with the substitution. And we get this over here. All right, so now we have switched back to index notation. So this term over here, we're going to call that lambda sub k. And at this point, we don't know yet that lambda sub k is a constant. Well, as a hint, it is a constant, but we don't know that yet. We don't know. We're still in the unknown phase, so we don't know if it's a function of x. We don't know if it's constant. We're not sure. Yet, at least. So here's what we have so far, displayed in a compact way, where lambda sub k is equal to that complicated expression, or summation. So what we have here now is a system of n minus m equations that we derived from the constraints, and we have a system of n equations that we derived from, that we derived. So what we have here is a system of equations. Initially, our unknowns would be all variables in x, but if we substitute in the n minus m parameterized variables in x into the n equations in the box, then we have m unknown variables from x and n minus m unknowns from the lambda case. Thus, we have n equations and m plus n minus m, which is equal to n unknowns. This means that we have n equations and n unknowns. So we can find unique values for all m independent variables in x and for all lambda k's. This means that the lambda k's must be constant. Remember how we said that we didn't know if they were constant or if they vary with x? Well, now we know that they are constants. Since we have unique values for all the independent variables in x, we can find unique values for all dependent variables in x using the equations in the box. At this point, we have solved for all variables in x, as well as all of the lambda k's. And we will call this solution x bar. And it represents the point at which the maximum/minimum resides in f of x, subject to the constraints described by g of x is equal to the 0 vector. So basically, we have those n minus m equations in the top box. We can get those from g of x is equal to 0. And what we have there on the bottom box is actually the gradient of f of x is the sum of all, from k is m plus 1 all the way to n, of lambda sub k times the gradient of g sub k of x. And this is all the information we need to solve for x bar. So we may also define a function called the Lagrangian function capital F, such that when the gradient of capital F is 0, the conditions are automatically satisfied. So to see this better, let's express things back in index form. So we want a function capital F such that when we take the gradient and set it to 0, it automatically satisfies the conditions below in that box. So the bottom condition on the left-hand side of the equation already looks like the elements in the gradient across x of capital F of x. But what about that other condition right there? G sub k of x is equal to 0. Well, let's finish the gradient. So far we've taken the gradients across the x's. Now let's take the gradient across the lambdas. That has to be equal to 0. So therefore, we say that the gradient across the lambdas of capital F is equal to g sub k of x. And there you have it. And the equation that satisfies these conditions is the Lagrangian. And also, there you have it. And so that is the end of this video. And I hope you enjoyed it. I actually had to remaster this video, or, do it again, but better, because I actually made a few mistakes. But I corrected those mistakes in this video. And so I think this video is so far my all-time favorite. I really liked making the video, and I think it's going to turn out really well. So have a great day, and I'll see you guys in the next video.